want to introduce chapter 4, which to me is the single most important chapter in the entire book. If you know this chapter, then you naturally, next thing that happens is you know alkene chemistry, you know alkyne chemistry, you know nucleophilic substitutions. So what is this? This is about acid-base. But not the kind of acid-base that like you taught yourself in a boring way. Like in Chem 2, you learn acid-base also. You first learn about rates of reaction and equilibria, and then after equilibria, you learn Ka, and it's just an icebox, right? To you, acid-base is find the pH, find the pH, find the pH. That's not what this is about. An acid is something that needs electrons, and a base is there to give it electrons, so it's all of chemistry. It's how things combine. Arrhenius defined an acid as something that increases H3O plus concentration. So something that increases H3O plus concentration is an acid. And a base is something that increases OH minus concentration. So why would Arrhenius say that? Well, because when you put HCl into water, there is, I'm going to write it as an equilibrium. It's not really an equilibrium. The reverse direction is negligible. But when you have HCl in water, it dissociates and gives you a chloride ion and H3O plus. And of course, the reverse direction is negligible, but HCl is therefore an acid because HCl increases the H3O plus concentration. It is an acid. On the other hand, if you have NH3 and you place that into water, then the NH3 associates, makes NH4 plus, but the key to this is that it also creates OH minus, and OH minus is the base. So NH3 raises the OH minus concentration. HCl raises the H3O plus concentration. Well, that is not wrong. That is a wonderful place to begin. But some other scientists came along, Bronsted and Lowry, and said, you know what? Let's have a more general definition because there's a little problem. If this is an acid and this is a base, then when I combine them in a tube, in a test tube, when I mix NH3 with HCl, what should we call that? Shouldn't we call that an acid-base reaction? If I have an acid and have a base, I mix them together, it's acid-base. Except look at this acid-base. It makes NH4 plus and Cl minus. There's no OH minus, there's no H3O plus in this reaction. Are they not acid-base anymore? They're acid-base. It's just the only reason the acid increased the H3O plus concentration is you put it in water. And the only reason the base increased the OH minus concentration is you put it in water. Take them out of water, they should still be called acid-base somehow, so we need a better reason to call them out, not the water reason. And Bronsted and Lowry said that an acid is a proton donor, and a base is a proton acceptor. So over here, if HCl is the acid, then H2O is the base in this acid-base reaction. And it's not that it's because it creates H3O plus, but because the acid gave up a proton to the base, and therefore you got H3O plus that way. Does everybody know why we call it a proton? I'm not sure everyone knows why we call it a proton. You just heard proton donor, proton acceptor in Gen Chem, and you rolled with it. You didn't stop to ask. If you stop to ask, fantastic. The first box on the periodic table is hydrogen. Hydrogen's got a 1,1. Oh, 1.007, but that's the number of protons, and that's the number of protons plus neutrons, so hydrogen has one proton. Hydrogen is a sphere, and in the middle it's got a proton, but the hydrogen atom is a neutral atom, so if it has one proton, it also has one electron, and that electron is floating around the nucleus, right? So if that's H, What is H plus? H plus means you removed an electron. So what do I have left if I remove an electron from H? Just a proton. So H plus is a proton. That's all that is, in case you never understood why it's called a proton donor or a proton acceptor. Think of this as an H plus and a Cl minus. So this acid has a proton connected to a chloride. And that proton jumps onto H2O, so it's H2O attached to a proton, so it's H3O plus. So that accepted the proton, that gave up the proton. Same thing here. That's the base. That means this is the acid. And the acid gave up the proton, the base took the proton, and that's why you got that, right? That makes a whole lot of sense. Proton donor, proton acceptor. Lewis said, you know what? We might be looking at this from the wrong direction. And all of you should have a problem with that also. This is orgo. How do you like these arrow pushes? Let's say there's H plus and a Cl minus. And there's H2O. When I say proton donor, proton acceptor, HCl is a proton donor, that terminology makes it feel like this H went onto here. How do you like my arrow push? Have you learned anything about resonance? If you have, can I start an arrow at an atom? What does an arrow depict? Electron movement. An arrow begins at dots or sticks. This arrow's all wrong. That's what Lewis said. It's just the arrows are Lewis structure, resonance, Lewis. Lewis said it's all wrong. You're looking at it the wrong side. Don't think about how the proton jumps. The proton's not jumping. The electrons are making bonds. An acid is not a proton, not a positive giver, but a opposite electron taker, electron acceptor. And a base is an electron donor. So when you revisit this acid-base reaction up there, and you draw it in a Lewis way, I'm going to draw the water first. Do you see I have the Lewis structure of H2O here? So I have H2O. I'm going to draw HCl. Here's HCl. There's the Lewis structure of HCl. And they react to give me Cl minus and H3O plus. Draw the Lewis structure of H3O plus. Draw the Lewis structure of Cl minus. And now, can you, using your knowledge of resonance, your knowledge of curved arrow, this is not resonance, but this is the first mechanism I'm putting on the board so far. A mechanism uses curved arrows to show how reactants react to become products. Could you use the resonance arrow type of an idea to figure out what arrows to push between these electrons that are in here to make the bonds and lone pairs and everything you see in the product? Do you realize, just start with the water, you've got oxygen with 2 bonds and 2 lone pairs, and now you've got oxygen with 3 bonds and a lone pair. What must have happened is one of the lone pairs became a bond. Could you picture this? If this lone pair became a bond and connected to the hydrogen, could that hydrogen have a bond to an oxygen and also a bond to a chlorine? But if you made a bond to the hydrogen from the oxygen, and you took this bond and broke it and put it onto the chlorine, do you see that's kind of like resonance? Remember we had like remember, if I take these electrons and bring them here, can I make another bond to that carbon? Not unless something gets out of the way. Do you see the connection between the two over here? A lone pair becomes a bond, and a bond becomes a lone pair. This is just like the first ABC thing that we've learned, right? Lone pair becomes a bond becomes a lone pair, and you get that result. We could take it one step further. This oxygen right here, this should be very interesting to you right now. I know that might have been a little boring, but isn't this a polar molecule with partial negative right here and partial positive on this side? Right? Do you remember there's a dipole vector this way, there's a dipole vector this way? It means this whole thing is polar in this direction? Okay. So you've got this H2O that's partial negative right here. What about HCl? HCl is partial positive, partial negative, right? Do you see if you've got a little like magnetic thing or like a little polar thing with a negative side and another little polar thing with a positive side, they'll kind of be attracted to each other and crash into each other? So that makes sense for why this oxygen lone pair crashes into this hydrogen. But it doesn't necessarily yet make sense why this bond moves out of the way until you realize this following thing. Let's investigate the HCl. There is a 1s orbital, a 1s orbital that the hydrogen atom is using. And there is an sp3 orbital that the chlorine is using, because think about it, it's sp3, do you see that? And they have between them an HCl sigma bond. Does everybody agree? From the hydrogen's perspective, which way is the sigma bond? It's going that way. Now, a very long time ago, feels like 5 million years ago, but it was just the beginning of this semester, like 5 weeks ago, I mentioned that like for sp3, for example, we're going to draw carbon's sp3 orbitals. We're not going to draw their antibonding orbitals that happen to be on the opposite side of where the sp3 orbitals are. For you, you should just realize that the bonding orbital is like 180 from the antibonding orbital, right? So from the hydrogen's perspective, this way on my board is the bonding orbital. So behind the hydrogen, on the opposite side, the back side of that hydrogen, is its antibonding orbital, right? What's the bond order right now of HCl before the oxygen interacts with it? What's the bond order? One bond, right? Do you see there's one bond? Because one electron and one electron make bonding. And 2 in the bonding minus 0 in the antibonding means a bond, right? Now when that oxygen goes and puts 2 electrons into hydrogen's antibonding orbital, that's like this oxygen just dropped 2 electrons into the antibonding orbital. What happens to the bond between H and Cl? There is no bond. That's why that bond just broke from H and Cl. We're going to apply that to nucleophilic substitution SN2, something called a backside attack, where the nucleophile puts electrons into the antibonding orbital of a carbon, breaking the carbon to leaving group bond. Make sense? We need to learn this first. This must be learned before SN2. For the rest of you, make sense? I have, there's Arrhenius, he said this. Arrhenius is specific compared to Bronsted and Lowry. Sort of like a chiral center is a specific kind of stereocenter, right? Arrhenius acid is a specific kind of Bronsted and Lowry acid. But Bronsted and Lowry acid is a specific kind of Lewis acid. Lewis encompasses everything. Lewis is watching the electrons transfer. For example, Bronsted and Lowry would not say whether this is an acid or a base. They have no comment because where's the protons? Do you see there's no H's on there? But Lewis would say this is absolutely an acid. Why is this a Lewis acid? Because that boron doesn't have an octet rule. It's missing electrons. So as an acid, it would be willing to accept electrons. Something that has electrons, like a base, like H2O, would be able to put electrons into that empty orbital, complete the octet rule, and that makes that an acid and that a base, you see? So you've got Lewis acids that have nothing to do with Arrhenius or Bronsted and Lowry. I have my version. I usually don't put my name up on the board for anything, but here's what I say. That an acid is electron poor. It doesn't seem like anything special. It's not. It's nothing special. It's not much different than what Lewis says, but just a little bit of a different feeling to it. That an acid is an electron acceptor, but really an acid is electron poor, and that's why it's accepting. And a base is electron rich. And in the chemistry world, nothing wants to be poor or rich. Like in our world, the rich want to get richer, the poor don't want to get poorer, but in chemistry, nothing wants to be positive and nothing wants to be negative. Everything wants to be in the middle and neutral. So what kind of charge would an acid have if it was not enough electrons? It could either be neutral, like HCl, right? Or positive. For example, over here, right? Do you see this thing as an acid? This HCl is neutral. And then if you go to this side, which of them is an acid? Probably not Cl minus, not just because you memorized as a conjugate base, but an acid being electron poor, not a lot of electrons, how could it have extra electrons and be negative? Like between these two, you would say the positive one is the one that doesn't have enough electrons, it's poor, right? Over here, you've got acid and base. You can't tell which one is which, but you could tell which one is which on this side. Do you see the N has a positive charge? If anything, that one is the electron poor one. The base is electron rich. That would make it neutral or negative. What if you have a messed up reaction like this? HCO3 minus plus HPO4 2 minus. And I ask you to complete this acid-base reaction. One of them has to be an acid. One of them has to be a base. And do you notice they're both electron rich? Still, with my terms over there, you're going to be able to figure out what's what. If you had to pick one of these as an acid, which one would you pick? Or if you had to pick one of them as a base, which one would you pick? I'd go with base, and I'd pick that one because it's definitely more rich than this is. Double minus is more minus than single minus. Does that make sense? So that would give me CO3 2 minus plus H2PO4 minus. Do you see this like bounces around which one is minus and which one's more minus? That makes some level of sense. We're going to be talking about inductive effects in this chapter, and they matter a whole lot. What is inductive effects? Do you remember that lesson that you were either here for in the weekend or watched the video of charge and charge dipole and dipole? Do you remember I talked about an induced dipole? An induced dipole is where you have something that's neutral next to a charge and they either pull electrons or push electrons and create partial. If you have a neutral substance next to a positive charge, the electrons in here get attracted to the positive, gather over here. This makes this partial negative, partial positive. So an induced scenario is being next to something and how you're influenced by that thing. Some acids are going to have groups next to them that pull electrons away or push electrons, and it's going to take a minute to understand this inductive effect. So that's not what I'm actually getting at. I'm actually getting at something else here, how to use this in yet another way. That is saying that it's sort of a number line. That idea is sort of a number line, that in the middle you have neutral, and as you go in this direction, let's say you become more electron rich, and as you go in this direction, you become more electron poor. Right? If you were over here, you're an acid. Why? Because you're on the electron poor side of things. You're an acid. Would you want somebody to come by and rob electrons from you or give you electrons? Who do you want to be? You want to be not poor or rich. You don't want to be, you want to be right in the middle. So if you're electron poor, you would like somebody to come in and donate some electrons so you kind of go towards this direction. Does every single molecule want a donation? If you're electron rich, if you're a base, do you want somebody to donate electron density to you? Wouldn't that make you more rich? You don't want to go that way. You want to go over here. You want to be at zero. You don't want to be rich. You don't want to be poor. Can we somehow hold that in our heads? I'm going to show you how to do a process, and you're going to be doing this for homework until you memorize a whole lot of things, especially the two of you. And then I'll explain why it works and how it works through the scope of Chapter 4. You're going to do this because you want to know what's a nucleophile and which one's a stronger, which one's a weaker nucleophile. There's no other way. So first we're going to write, lesson's over in like 10 minutes. First, we're going, it's been like 2 hours. Right? Am I wrong? What time are we supposed to be done? 1:30? It's like 1:28. We started a few minutes late. Okay. So I'm going to draw a table of acids, their conjugate base, and pKa's. And pKa's are really important for us, and we're going to memorize a whole boatload of pKa's. But you're not going to memorize it like sit there and try to memorize it. That's the worst way to memorize it, to try to memorize. Another worst way to do things in Orgo is flashcards. If you want to destroy yourself, use flashcards. If you've been using flashcards, stop. There's no better way to destroy yourself than using flashcards, because that makes you memorize a picture. So on your picture, you're going to write RC double bond OOH and call that a carboxylic acid. And on your exam, your professor is going to write, tell me the name of this functional group, and you're going to say, I have no idea, because you burned that picture in your brain, and this is a carboxylic acid too. So unless you could draw every kind of picture for every kind of molecule, flashcards are not helping you. They're just hindering you. The best way is to practice problems and to keep constantly having to recall things, because that's the skill you're going to have on an exam. Unless your professor is going to say, this exam is flashcards. I'm going to throw flashcards at you and you write the name on the back of that. Then you have to practice flashcards. You see what I'm saying? Otherwise, flashcards don't work at all. They're training you for the wrong skill. Plus, I could prove that the way that memory is stored, the way memory works is you don't need to put it back into your head. The first time you see something, I could prove this to you, there's medical cases that prove this. The first time you see something, it goes somewhere into your brain. And the problem is not to put it into your head again, to see it again. The problem is to extract it. I've had students listen to my lesson, like you could go home and watch my lesson 10 times. That doesn't mean you know it. It's when you take that and apply it to homework problems and are forced to extract it, that's when you start knowing it. So I'm going to give you a table of pKa's. You're going to use them in a particular way that I'm showing you to solve problems, and then you're done solving problems when you no longer have to look at the table. When you've done so many problems that the table is just like in your head, that you don't, you know what I mean? Have you done enough resonance or RNS problems that you don't have to look at the periodic table much to figure out like which is a higher priority, chlorine or iodine or whatever? You know you've done enough problems when you don't have to look at the periodic table for that. You know you're on track. First, I said I'm going to give you a table. Going to write in a second. I said I'm going to give you a table of acid and conjugate base. Do we know how to deal with acid and conjugate base? If I have a molecule that I draw, and I ask you to write its conjugate acid or conjugate base, to take a molecule and draw its conjugate base means remove H+. To draw a conjugate acid, that means add H+. There are some of you that are like, why is he writing this? We know this. Okay. What is the conjugate acid of HF? If you said F-, you're not paying attention. If I take this and make the conjugate base of it, I remove an H+. So you're thinking about this as an H+ and an F-. The conjugate base is F-. That's the conjugate base. But I asked for a conjugate acid. I need to go in the other direction. I need to add an H+. So what is the conjugate acid of HF? It's H2F+. What's the conjugate acid of H2F+? Just add on another H+. H3F, and if I had a plus, but I put another H with a plus, so it's 2+. What's the conjugate acid of H3F 2+? H4F 3+. What's the conjugate acid of H4F 3+? There is no such thing. Does anybody know why? Because here's why. Here's why. It's the Lewis structure of it. It's the Lewis structure of it. Look, when I have HF and I draw F-, this is what I drew. And if I have HF and I draw H2F plus, this is what I draw. And the plus is just a formal charge. That's H2F plus. What's H3F2 plus? F is in the 7th column, minus 1, 2, 3, 4, 5. 7 minus 5 is plus 2. What's H4F3 plus? Do you realize why there's no more conjugate acids and no more lone pairs? It is the lone pair that attaches to the H plus. And when you remove an H plus, you leave a lone pair from that bond. Right? So if I remove an H plus, the bond stays with a lone pair. Here's an extremely important list. Requires a fresh marker. We start with HI. This is going to be a list of acid. There's an acid, conjugate base, and the pKa of the acid. Of course, I'm going to really have to describe what pKa is. We'll do that in the next lesson. But if that's the acid, then I minus is the base. After HI, HBr. After HBr, HCl. After HCl, H3O plus. After H3O plus, I could put a whole bunch of things, but I'm going to put HF. Some of you are going to look at this list and be like, oh my God, it's such an enormous list. This is the concise, short version. Don't worry, this will be in your head in a week, I hope, if you practice it right, and you'll realize how important it was that I made you do this. After HF is H connected to a carboxylic acid group, so this is formic acid. We talked about formic acid. Red ants? Okay. After formic acid, I'm going to put R instead of that H, and a carboxylic acid group, so that's carboxylic acids in general. This one is formic acid, and this is generalized carboxylic acids. Okay? After that, I'm putting something in here that I used to not put on the list, but I'm going to include it because I want this in your head for biochem. So if you want to ignore any one of the numbers right now, it's this one, although some professors like to ask questions about this one. It's H2CO3. After that, this list, by the way, is going to be longer than this. I'm going to have to like spill it over onto another continuation of the list. After this is H, no, not H. I'm going to go R. RSH. After RSH, it's going to be NH4 plus. After NH4 plus, HCN. After HCN, H2O. After H2O, ROH. We know what an R is, right? It's a carbon or carbon group, so this is hydrogen, oxygen, hydrogen. This is carbon, oxygen, hydrogen. So this is water, but these are alcohols. Right? After ROH, it's going to be some group, some carbon group, then a carbon, triple bond carbon with a hydrogen. After that is going to be NH3. It's going on forever and ever, right? It's only two more. After NH3, this one's very difficult to depict. What I have depicted in here is an sp carbon, a hydrogen on an sp carbon. There's two more that I want to depict. I want to depict a hydrogen on an sp2 carbon and a hydrogen on an sp3 carbon, right? So before you draw it, look what I'm trying to draw. A hydrogen on a carbon that's got like a double bond. And then I want to draw a hydrogen on a carbon that has like just all single bonds, right? See how, but if I drew that, and then and I just drew this, you wouldn't really understand what I'm talking about. So I guess it's connected to another carbon and then more stuff. So over here, this is, I don't know, there's like a carbon and there's a carbon here and more carbons or hydrogen. Like these don't have to be carbons, they could be hydrogens. The only important thing is like it's an alkene hydrogen. So you got an alkyne hydrogen, an alkene hydrogen, and then, I don't know, an alkane hydrogen, CH with like, I don't know, R, more R groups. Do you see this? Okay, what is the conjugate base of Hbr? Br minus. Conjugate base of HCl is Cl minus. Conjugate base of H3O plus. H3O plus, take off an H, it's H2O. Conjugate base of HF is F minus. Conjugate base of this, which hydrogen do we remove? Well, it's the one attached to the oxygen. H, carboxylic acid, but it's a carboxylate actually, and it'll have resonance. This also is very similar. H2CO3, that's HCO3 minus. RSH is RS minus. NH4, NH3, thank you. HCN, CN minus. H2O, OH minus. ROH, RO minus. The alkyne is going to give me an alkyne anion. NH3 is a base. I put it in the acid column. What kind of an acid is a base? What kind of a rock is a car? It's not, right? If I expect, if I'm asking what kind of an acid this is, it's a very, very incredibly, impossibly weak acid because it's a base. But yet, nonetheless, you could rip off a hydrogen from there and make NH2 minus. Do you realize what this is going to look like if I rip off a hydrogen from here? I'm going to leave behind the bond as a pair of electrons, so it's going to be R connected to C. C, there's going to be an R group here, there's going to be an R group here, but instead of a bond to hydrogen, it'll be two dots and a negative charge. This is going to be a C with its R groups. And up there, instead of a bond to a hydrogen, it'll be two dots and a negative charge. The pKa. So you should draw, I should have drawn something above this and written above this pKa acid conjugate base, right? The pKa of HI is -9. Could you have a negative pK? Yep, absolutely. We'll talk about that next time. The pK of HBr is -7. HCl is -5. In your textbooks, no matter which textbook you have, the pK of H3O plus is -1.74. That's wrong, and it should be 0. So I'm going to call out every textbook ever written on organic chemistry and say they're all wrong. Every single one of them. I don't care who your professor is. I don't care what their opinion on this is. That's a 0, and I will prove it in our maybe next lesson or the lesson after that. I've been proving this for years. Most students agree with me, and they're the ones who become doctors. You don't have to agree with me. You could stay not a doctor. If you, after our discussion on it, if you disagree with me, fine. But I'd like to have a conversation with you and understand why, how it's possible. There's things that you could agree and disagree with me with, but if you hear the argument and work out the math and still disagree with me, I want to see why, because I guarantee every single person will agree with me and then say, why is it not in textbooks? Why are the Orgo books wrong? Because it is in some textbooks, but they just happen to not be organic chemistry textbooks. For some reason, organic chemists took a number that physical chemists made an error on. And how do I know there's an error? Because I'm also a physical chemist. And we know where we made a mistake. And I don't know why they ran with that number. But anyway, it's not negative 1.74, it's 0. How about for your purposes? Nobody will ever ask you what the numerical value of pKa's are. I have yet to see. But we need to use them for something. And whether you use 0 or negative 1.74, you'll almost every single time get the same answer. It doesn't matter. It's just there's a very strong concept here that's important. HF is around 3. Formic acid is 3.8. This is more like 3.5, but I'm going to just call it 3 just to make it lower than this. This is carboxylic acids in general, and they are between 4 and 5. For example, if you remember anything about Chem 2, acetic acid had a pK of 4.76 because it had a Ka of 1.8 times 10 to the negative fifth. That was the only number that you've seen over and over again on every exam. 1.8 times 10 to the negative fifth. Anybody remember this number? H2CO3 is about 6.1. Just remember 6. It doesn't matter. RSH is approximately 8. Ammonium has a pK of 9.2. HCN has a pK of 10. HCN, 10. That rhymes. Something like that. Water has a pKa of 15.7. The same physical chemists that made an error with H3O plus made an error with water. You could just say water's pK is its autoionization, which is 1.0 times 10 to the negative 14th. Take the negative log of that, and the answer is 14. So I should cross that out and write 14, just like I crossed that out and wrote 0. I'm going to leave that number because there's at least some discussion you could have with that number. I don't agree with that number, but I'm going to leave it because there's at least a theory of why it could maybe not be 14. There's no logical person who knows anything about energy that can dispute the 0 for this. There's no dispute. It's impossible. What if we learn something new? Yeah, whatever. I will wager that no matter what we ever learn in the future of anything, that can't be other than 0, because we'd have to live in a different universe. In our universe, we have certain rules on entropy and enthalpy, and you'll hear my argument. ROH is 16 to 18. You know what you gather from my table? Here's an interesting detail. When you switch a hydrogen that's unrelated to the group that's the acid. Here, what's the group that's the acid? The carboxylic acid is the acid, right? And here, the carboxylic acid is the acid. Do you see the carboxylic acid is the acid? That's what lost the hydrogen. Next to them is a hydrogen versus an R group. When you switch a hydrogen to an R group, the pK goes up about a unit. And over here, it's HOH versus ROH. Now, the H is on this side that we're losing, but on the other side, it's an H versus an R. And when you switch the H to an R, the pK goes up by about 1 unit. Do you see that? That's something called the inductive effect, and I cooked it into this table. I'm putting that in there on purpose. The pK of this is around 25. The pKa of ammonia is 38. Once you get the numbers past 25, there's lots of questionable, like you can't really measure a number like 25 or above, because we'll learn what a pKa is and how impossible it is to measure it, so it's very big estimates. So there are books that call ammonia over here not 38, but 41, 42. That's totally fine, whatever number you want to use. I like 38 for biochem reason, but I'm not saying my number's right and those numbers are wrong. Anywhere from 38 and above, I have no idea what the exact number is. I do know that this is approximately the same as this. I just like the order of this first, then this. And sp2, carbon's hydrogen, is around 40. But again, in some books, you might see it as 45. We can't, whatever book you want to use, you quote that book. Like, there is no literature value. You know, when you're writing a report, by the way, I teach analytical chem and I make my students write reports in a particular way, you never quote the literature value. You quote a value and say by that person's paper or that book or that lab, you have a citation, not the literature value. So anything above 25 is very sketchy. To me, this number is 50 plus. There's books that say it's 60, 65. It doesn't matter. It's the biggest number on the entire list. You know what I mean? So whether I use 1 million here or 50, it's still bigger than all the other numbers. And it'll be useful to... How do you memorize this? I'll show you one example of what I want you to do. Pick any acid, random acid, I don't know, that, and any base, any random base. So I pick one of the acid column, I'm going to pick something from the base column. Random. And I'm going to draw the base. See the base? And the acid. And I'm going to write equilibrium arrows. Crap, I have to erase them. Let me move it over a little bit. Okay, here's the base. Here's the acid. You draw equilibrium arrows. And you draw for the base, you draw its conjugate acid. And for the acid, you draw its conjugate base. Can everyone agree that I at least drew the conjugate acids and bases, right? Okay, what's the process? The process is pick any acid, you draw it down, draw it. Pick any base, you draw it. And then for each, draw their conjugates. That's step one. Step two, draw the correct arrow pushing in the reactant side to lead to the product side. And the arrow pushing is the base uses its extra electrons to make a bond to the hydrogen that we say is the acidic hydrogen and break off the bond onto the leaving group. That's always going to be. It's always going to be that it's a Lewis idea, that the electron-rich base is going to use its electrons to make a bond to the hydrogen that is the acid. In the nucleophilic substitution chapter, we're going to replace a hydrogen with a carbon and call that a nucleophilic substitution. And every base that we have is a nucleophile. And the stronger the base, the stronger the nucleophile. And it's going to SN2 backside attack and kick off the leaving group. And that's what we're going to deal with in a chapter or two. Okay, so step one was to draw the random acid and base. Step two was to draw their conjugates. Step three was to draw the arrows, the correct arrows to push in here to lead to here. And step four is to figure out the direction of this equilibrium. And at first that would be tricky, but I have to remind you of something in order. Some of you were good Gen Chem students, so I think you are going to know what I'm talking about. Do you remember in Chem 1, way back in Chem 1, you would figure out if a reaction happened by doing a metathesis and looking at a solubility table? Do you remember if you had something like LiCl plus AgNO3, and they said, complete this reaction and tell me if it occurs? So you would switch partners, metal, nonmetal, metal, nonmetal. So you would write LiNO3, and you would write AgCl. And then you'd look up a solubility table to see whether it occurred. Just because you switch partners doesn't mean something happened. But on the solubility table, you saw that chlorides are soluble unless they're connected to Ag, Hg, or Pb. And all nitrates are soluble. So this is aqueous, this is aqueous, this is aqueous, and this is solid. And now we found that a reaction did happen. That Cl minus plus Ag plus made AgCl. Does anybody remember that? Okay. We're going to do the same thing here. Same idea. Can you have this in your head? Can you follow what I'm showing you? Just because I drew a base and an acid and drew their conjugates doesn't mean that a reaction happened, because in this direction it's an acid-base reaction, but in the reverse direction it's an acid-base reaction, and I want to know which is the real direction of the acid-base. If I mix these two, are they going to react? Or if I mix these two, are they going to react? Because some side of this is higher in energy and some side of this is lower in energy. So I need to find the direction of the equilibrium, and we'll explain why this works, but this is the easy way to do it. It's using the pKa's. What is the acid on this side of the equilibrium? The answer is HF, right? Do you all see it? Underneath the acid on one side of the equilibrium, when you find the acid, write its pKa number. Its pKa is 3. Do you see that? Go to the other side of the equilibrium and find the pKa of the acid. Again, pKa of the, not the base, you're ignoring the base for now. The acid, RSH. RSH is an 8, right? Draw an arrow from the smaller to the bigger number. When you draw an arrow from the smaller to the bigger number, that's the direction of the equilibrium. What that means is, If I had RS minus and HF and I put them into a container, they would react and become RSH and F minus. But if I put RSH and F minus into a container, they're already there. They're not going anywhere. This is the direction they become. For example, if I mix methane and oxygen, they combust and become CO2 and H2O. I can't mix CO2 and H2O and suddenly get methane and oxygen, right? They go in this direction, not that direction. Do you hear what I'm saying? Why does HCl fully dissociate in water? Why does HCl dissociate in water? If that's the acid, then it makes Cl minus conjugate base. If that's the base, it makes H3O plus conjugate acid. What's the direction of this equilibrium? It's to the right. Irreversible, right? Because you know that dissociates. But why don't we use this? What's the conjugate acid on this side? It's HCl, not the water. The water's acting like HCl is a -5. What's the acid on this side? H3O plus. It doesn't matter if you use their number, -1.74, or my number, 0. From the smaller to the bigger number, it goes in this direction. And we're actually going to learn to calculate a KEQ from this. And the KEQ is 1 times 10 to the delta pKa. So the KEQ is 1 times 10 to the pK here minus the pK here. What's the pK there minus the pK here? 0 minus -5. It's 5, right? The equilibrium constant is 10 to the 5th in this direction. The equilibrium constant is 100,000 products for every reactant. Doesn't that mean that reactants are negligible and it fully dissociates? Didn't we learn that 500 times more makes the other one negligible? Does acetic acid dissociate a lot in water? Is acetic acid a strong acid? That's rough. It's a weak acid. That was all of Chem 2. All of Chem 2 was learning acetic acid is a weak acid. HC2H3O2. Okay? If that's an acid, I'm going to dissociate it and make the conjugate base. And that's the base. I'm going to make the conjugate acid. What's the pK of the acid on this side? You don't know the exact number, but what is it between? 4 to 5. It's RCOOH. Do you see that's a carbon over there? COOH. RCOOH. Oh, by the way, put that on a flashcard and annihilate yourself. Because on a flashcard it's going to say RCOOH, but the molecule your professor is going to give you is a transdecalin with a COOH. And ask you what's the pKa of this thing. Do you see? And you're going to be all confused. There's nothing to be confused. Find the functional group and remember my functional groups and you're good. This is a carboxylic acid attached to an R group. This is a carboxylic acid attached to an R group. It's between 4 and 5. There's a carboxylic acid attached to an R group. You know what the simplest thing is? Since it's between 4 and 5, just call it 4.5. It's right in the middle. You're not going to be off. Okay, so the acid on this side is 4.5. What's the acid on that side? What's the acid on this side? It's a 0, right? So which way does this equilibrium go? This equilibrium goes left. The KEQ is 1 times 10 to that minus this number. So it's 1 times 10 to, let's say, the -4th, -5th. Do you see how little products there are for every reactant? And that means that this barely dissociates. 1 out of every 1,000, 1 out of every 10,000 molecules dissociates. It's a weak acid. I need you to know these pKa's by just practicing random. What'll HBr and I- do? What'll this and this do? What'll this and this do? What'll one of these and one of those do? Just keep mixing back and forth till you don't have to look at the pKa table. Because the second part of this chapter is to learn the 5 effects: size, resonance, inductive effect, electronegativity of the atom holding the charge, and hybridization. And we're going to learn those effects by first knowing the answer. We're cheating. This is cheating. Knowing the pKa's means you know which direction the equilibrium goes without knowing which effect is stronger than which effect. So we're going to know which direction the equilibrium goes and then find an effect that supports our argument. You will see later how that's cheating if you... So cheat with me. Thank you for your participation. Hit the success button.